Hello and welcome to another episode of the Construction Corner podcast. I'm Dylan. I'm your host, and today, guys, we are joined by Ryan Easterling, who is with Burns and McDonnell. He's an electrical department manager in the power distribution and generation side of things, which I'm super excited to talk about. And he also went to my alma mater of Rose-Hulman, which also is a big kudos on that side of things. We don't meet too many Rose grads out here in the wild. So, um, with that, Ryan, great to have you on.
Yeah, great to be on. Thanks for the invite and great to do this right before Thanksgiving.
Yeah, man, it's perfect timing to do a lot of this stuff. Um, and have these conversations, for everybody kind of thinking about the new year. And with you being on the power and generation side, which I know we'll get into, kind of super excited to hear what's happening in that market that feeds all the downstream stuff that most of the other guests are going to work on.
Absolutely. Yeah, I mean it's as busy of a time as I can remember in my 13 plus year career. Not just now, but looking ahead to the next 5 years, just the sheer volume of projects that are coming up, especially with the advent of AI and data centers. Just the amount of infrastructure that's required to support all that is really driving this market. It's an exciting time to be in it.
Yeah, for sure. Well, speaking of new new starts or new beginnings in a way for a whole new market segment, but how did you get into engineering? Like what made you go to engineering school?
Yeah, it's kind of funny. Growing up, you could probably empathize with this, but it was just I always wanted to try and figure out how things worked. It's a little bit of the Dilbert syndrome where you're taking things apart and putting them back together, and like I started that at a very young age, and it wasn't just how like that things work. It was I wanted to figure out how things worked, or if they broke, like how do I fix it? I vividly remember. I think it was my freshman year of college. I came home, and this was, I mean, after I'd kind of decided on the engineering path, but I came home and my parents were like, "Hey, the circuit board on the furnace took a dump, and we have another one sitting on the porch, and we won't be home for a few hours." And I was like, "Well, I'm just gonna get this thing installed because I don't want the house to be cold." And like, I was like, "Holy crap, that's being an engineer. Like, you figure it out, you solve problems." And they were like, "Oh, we didn't think you'd have this done." I was like, "Well, yeah, I didn't want a cold house when you guys got home, but." Um, how I actually got into engineering in the first place, though, it's funny. I had a high school teacher who saw it in me, but ironically, the person who really probably played the biggest role in me landing at Rose-Hulman and going that engineering route was my sophomore English teacher. So her husband was the football coach at my high school, and he played football back in the 70s with the associate dean of students at Rose-Hulman at the time both of us were there, Tom Miller. So Tom Miller was an alum of my high school as well, and so when I got linked up with Rose-Hulman, I fell in love with the school. I looked at several great engineering programs coming out of high school, but it felt like Rose just really resonated with me well, and it really supported and fanned the flame of that spark I had for engineering, and just the rest is kind of history.
Yeah, I can totally relate to most of that. So like I lived off the grid in high school. So like before it was ever cool or anything else in Oregon, mainly because we got 40 acres, right? Like that was the whole purpose of us living where we did is we had 40 acres. Yeah, we had cattle and sheep, pigs, like all the 4-H animals. And so, but I had solar, wind, hydro. We had a diesel generator, battery banks, an inverter to do all of it. So it's kind of funny. Like I lived off the grid before. It was like cool to have solar panels on your roof, back in whatever 2003, four. So kind of interesting for me. And my neighbor he was one of the lead engineers at Livermore National Labs on the laser program back in the 70s and 80s. And so kind of, that prompted me to go to engineering school. It's like, okay, here's the path, here's what we could do. And then kind of everything was history from there.
So you hipstered the microgrid.
Yeah.
I've been wanting to use that word for a while.
Yeah.
But
I mean, it's one of those like yeah, I mean, it was right. Like we had our own, small little windmill with 3-foot blades. But the problem with a small windmill when you live on the Oregon coast is you get 100+ mile an hour winds. And so the blades would bend so far and the tips would actually break the sound barrier. And then they'd bend and snap against the pole that we had that's 110 feet in the air. So you'd have, I mean, so wind was like it's cool, but a lot of problems with that blades and trying to replace it if anything breaks. Hydro worked great for 6, 8 months of the year, but on the Oregon coast, like yes, we get 100 inches of rain. However, that's only in a 6 month time span. The rest of it, there's nothing, and then you have pipe blowouts and maintenance of that system. Right, we had a pond that fed it with a penstock down to basically a car alternator is what turned with little like teacups on the end for it. So a lot of it, is built that you go to engineering school and you're like, oh, this is, all the other stuff that we talk about. And this is now we learn all the math behind it versus, I learned how it got built, on a very small scale compared to like I've been in some of the dams that are on the Columbia with however many megawatt turbines are sitting, in the particular dam that I went into, and it's like cool versus standing over a dam turbine and like, oh wow, this is like way bigger, that you're standing in and it's massive.
Yeah, it's interesting because over the course of my career, I've had an opportunity to work at power plants that have generators that are in the kilowatt range, like an old hydro from like the 1920s, 1910s that had been renovated and was shown as a museum. And then I've been at plants where there's 600, 700 megawatt steam fired turbines. Career hasn't taken me through the nuclear space yet, but I think it's headed that way. And we'll probably touch on that in a little while. But seeing just the scale of it all. I mean, you do science projects in science classes growing up where it's like, oh, we turn this little motor with a battery. And then you get to this and you have a much greater appreciation for the sheer power that is behind all of this with the amount of steam, and you see the amount of coal that's getting burned or the amount of natural gas and the weight of all the iron that's in the copper that's spinning, and it's pretty eye-opening. So for anybody that, when you're going high school to college to the professional sector, um, probably a piece of advice is just like be receptive to like learning those things, getting those experiences, because seeing is believing. We're at my company, we're really big on people getting out into the field and seeing the projects that they're working on. And it's because you not only have an appreciation for what you're doing, but you learn so much from getting out in the field and actually seeing it with your eyes. Because you can stare at a sheet of paper all day, but until you see what really all this stuff looks like as it's getting built and once it's built and in operation, you really don't have an appreciation for it.
That's so true. From anything from just conduit getting installed to what a 2 megawatt generator looks like to, the size of projects that you're on the generation side, what is the pipeline for natural gas look like coming in to feed these steam turbines? Like how many feet in diameter are these pipelines that come in? It's massive, and that's such a powerful thing. Like I was having a conversation with somebody about generators for a data center, and they were asking, hey, are these natural gas or is that all diesel? And I was like, well, typically we go diesel, but they could be natural gas. It'd just be we'd have to put a pipeline in for the 102 megawatt generators we'd have to line up outside of this thing, to feed them all. But sure, and it's really the entitlements and easements that you'd have to go through to put a pipeline in for how much natural gas you'd need.
Yeah, and what's even beyond just the boom in power generation is all the infrastructure that's going to have to surround it. And data centers are kind of changing the game as far as how all that happens because nowadays you can see it takes a while to get power interconnects for grid interconnects in a lot of these places. I mean, we're seeing unprecedented lead times now for key electrical equipment that is, in the past may have been months, is now well in over a year, 2 years, or like some of the high voltage equipment is pushing 4 and 5 years. There are turbine suppliers out there, gas turbine suppliers that are taking orders for like 2030s delivery, which is just crazy. But the amount of buyout that's happening between both the power generation market and the data center market is at an all-time high. And so I touched on this earlier. It's an exciting time to be in this market, but it's also a challenging time because the supply chain is being tested in ways that it hasn't in the past.
Yeah. Man, I so much want to dive into this, but let's back up real quick. And what being at Rose, going and obviously best engineering school in the country. I can say that with all bias. But with that, and going to Burns McDonnell, what was kind of that transition, or what kind of pushed you in going to work for them?
It was interesting. So I interned for 2 summers with a company in a completely different sector. I was doing electrical engineering. Some of it was like more process engineering, but I was doing electrical for something more in the agribusiness sector. And what ultimately led me to Burns McDonnell was kind of serendipitous, really. But uh, I had been there. I did 2 summers with them. It was a company I was really familiar with growing up, where I did, and you know, I enjoyed it, but it wasn't really what I felt like I was called to do long term in my career. And I wrapped up a little early with one of the projects I was doing my second internship, and was like, "Hey, I've done some electrical study work in some of my classes, and you guys mentioned that you've got or had some issues with selective tripping on some of the electrical distribution in the plant." I was like, "You guys mind if I take a look at like whatever study materials you have, like for your electrical system models?" And so got a hold of a binder that was in the library at the plant, and it had Burns McDonnell's logo on it. And I was like, "Well, this is kind of what I want to do." And ultimately ended up seeking out Burns McDonnell. Ended up interviewing with them in the fall of 2011, and wound up with an offer to start in summer of 2012 in the Chicagoland area. And I've only ever been at Burns McDonnell. I could see both pros and cons of that, but I really enjoy it here. It's a great company to work for. I've talked with some people from other locations, and I can't speak for their experiences, but a lot of the people that have been elsewhere and come here have really valued the company. We're 100% employee owned, so I've really liked that part of it because you got a lot of skin in the game because everyone's success is mutual, and so we see the fruits of our own success and our own labor. But it's been great. It's definitely been challenging, but it's also equal parts rewarding, which has been a great part of this career so far.
That's pretty cool, man. All I did was power studies, or that was my first two internships, and then 2.5 years out of school was doing power system studies, going in plants, and doing all the arc flash studies, coordination, short circuit studies. I got kind of tired of it after a little while, and went over to the architecture side. But yeah, I mean, some people, and I mean, being in the utility sector, those are much different problems that you run into versus on the industrial side.
Yeah, I mean it's been no shortage of fun stuff to work on over the years, but I think one of the cool things too is over the course of my career, I've had an opportunity to work on a lot of different subject matter. I mean, the bread and butter has been power generation, but we've dabbled in other markets. Still associated with power in one way or another, but starting out, did a lot of kind of peaker type generation, so reciprocating engines for the first 4 or 5 years I was here. And then for a little bit did when the CCR ELG rules, which is like coal combustion residuals and all the effluent limits on wastewater, did a lot of large projects for those at some coal facilities for about 2 or 3 years. Towards the end of the 2010s, I actually did a lot of engineering support for utility separation for plants that were being retired and demoed, which was actually a lot of fun because it kind of forces you to reverse engineer power plants, especially when the documentation at some of the older plants is not as great. You get to see a lot of different clients, a lot of different ways that power plants were built. So that was a cool opportunity, not only to get to see some older facilities, some more unique facilities, but also get an understanding of how back in like the 50s, 60s, 70s, these plants were engineered and built, because it has changed a lot since then. But there are things I was able to take away from each of those different facilities that I still use today in my arsenal, which is a super valuable thing. Um, Done a few electrical upgrades here and there, but the last couple of years I've been largely focused on liquefied natural gas peak shaving, which is for those that aren't familiar, essentially you take natural gas off the pipeline when demand is low and the prices are low, run it through a refrigerant process, liquefy it, and it stores in a large tank. So we're talking on the order of 1 to 2 billion cubic foot equivalent. So just to clarify here, it's not billions of cubic feet. That would be enormous. But what it is natural gas in liquid form is 1/600th of the volume of natural gas in its gaseous form, and therefore you can store it at a much higher energy density in liquid form. And so they'll store it during times where demand is low, and then send it out, vaporize it either for commercial, residential, or power generation use whenever the demand is there.
That's pretty cool. That's a good market efficiency right there.
Yeah,
Uh,
it's almost like a natural gas battery.
no,
So
that's really cool. In the plants that just to double click on the plants that you were doing demo work or decommissioning for, was that to you basically demo them out and then build back in the same footprint for them, or were they just complete decommissioning of that site?
it was a little bit of both, but for the most part, it was just demo and retire. So the sites were being cleared out. In a lot of cases, there were land deals with either cities or developers that would repurpose that land because, as you can imagine, too, coal facilities, especially that had been around since the 50s or 60s, there are like millions of cubic yards of waste ash that are on those sites that are in impoundments, and so. Um, a lot of those have, continuous water monitoring, groundwater monitoring that have to take place. But in most cases, they would just demo them to grade, maybe a little bit below grade, and either repurpose them. Though there were some facilities because of the way the interconnect agreements work that they could actually do what's called a replacement interconnect. And so because you've already got all the transmission infrastructure run to those facilities, they were able to install new generation on those sites, more modern generation, which if you think about it, it's crazy when you look at it, an older coal plant that's 30 megawatts, 50 megawatts, it's got a whole bunch of conveyors, coal piles, crushers, big pumps for steam, the boiler and everything, and it can get replaced by a real small package turbine with far less auxiliary equipment. And just the way that technology has evolved over the years is pretty amazing.
Yeah, that's pretty cool. That's a cool upgrade that you could do it in a smaller footprint. Granted, you don't if you're doing it with gas, right? You have a pipeline coming in, you don't need all the
Hmm.
yard space for storage, basically, or
Right.
disposal. Um,
Right.
but that's
Yeah.
that's pretty cool. Those are cool projects. All right. To probably the because clearly you like the industry and it's, getting more exciting. So let's talk about the exciting stuff of power generation. So for all the listeners too, like this is pretty unique for this show. Like I don't always get to talk to other electrical guys, and especially in the power field, that are, on the front end of everything that is coming, right? With AIs, data centers, and those types of projects, that we're working on, big industrial and manufacturing plants, hospitals. Like you guys are the front end infrastructure, right? So you're seeing the boom well before everybody else, or at least what's coming from the biggest users of power right now, which is data centers. That's the big one, and there's more and more of them that are going to get put in, and at crazy scales. We're seeing gigawatt data centers get at least publicized, and a lot of them are getting put in. So with that, like, let's talk about some of the um, infrastructure pieces that somebody would need to go through, and maybe what a little bit of that process looks like for some of these users and what they go through. Um, I know one of the first things that you probably either do or the utility knows is just the study on the utility side, right? Of whether they can even the feasibility study for them, right? So talking to the utility and whether they can even put in some of these plants. I know that's maybe not in your purview, but I guess walk us through the process on some of the what utilities would look for in putting another power plant in, or those kind of conversations down, this general line.
Sure. So a lot of the utilities, especially the larger public utilities, put out what's called an IRP, or it's an integrated resource plans. They're always looking 5, 10, 20 years down the line because not only are they looking at end of life for their existing assets, but they're also looking at what is our load demand going to be 5, 10, 15, 20 years out? What sort of profile are we going to have between, especially now, a lot of the larger utilities are investing quite a bit in renewables, in energy storage. And so they're putting those out there. We keep an eye on a lot of that stuff as well. We have as also an arm of our business. that does a lot of that study. They come alongside utilities and help them kind of figure out what's the right mix of utility. They can look at their network systems, look at, wait, what's the ideal location, both from a land access, infrastructure, and economy standpoint, and help them site utilities. And that's especially important for solar, where you're talking about very large plots of land. But even then, just where you interconnect on the line and how that plays into supporting the electrical system is really important. How close are you to what the end user might be, which now is becoming more and more critical with data centers becoming so prevalent. And so, they're always looking out 5, 10, 15 years down the line, especially as they have to allocate funds for it, make sure that they're doing right by ratepayers, especially for public utilities. Private ones, obviously, you've got a little bit more flexibility, but still have to follow all the interconnect regulations. But they're planning ahead, trying to figure out, hey, what's our load demand going to be by this date? And now, as I was mentioning earlier, with lead times and project delivery times pushing out a little bit, not only are they having to start earlier, but we're having to get more creative with how we schedule, sequence, and engineer our projects so that we can meet those delivery dates. And sometimes it's just a matter of saying, hey, based on what we're seeing, we can hit X date. Like, you may want it by such and such, but it might be another year or two just based on these two components. Or are there creative ways that we can either repurpose something, or maybe there's a production slot that's available with this vendor that we could slide into and try and hit those dates. But it's interesting, and I would say it was right around the time of COVID. We've had to kind of pivot how we approach projects from a schedule, execution, design standpoint. And then the other part of it is, over the last 10 years, my company in specific has really grown our construction capabilities. And so we are becoming more and more prevalent in the EPC space in power. And so the way we execute has changed from, in the past, maybe being more of an engineering and design only firm, to where we're now having to think through things from a construction lens. And so that transition, I think, has challenged us to think differently, but also allowed us to take ourselves to another level.
Yeah, I mean, so like for us on the engineering side, like all we do is work with electrical contractors. So that gives us the lens into the procurement side of it, even though we're not procuring anything per se. We're directly involved in all the procurement conversations of who can get what, talking to vendors, on behalf of our clients and what gear they can get, when they can get it, especially not so much on like the anything under 600 volt category, but in the medium voltage category, because now you have somewhat fewer options, especially you get above 15 kV. Like your standard manufacturers aren't always playing ball in that 25 kV and up category. So then you start getting into different manufacturers or very specialty guys in that medium voltage world. And again, above 15 kV, like 13 to 8, pretty standard for even your Eaton Snyders, those guys of the world. It's once you get past that it starts to be a procurement problem, or you better know the right guys to get you slotted for some of that stuff. So we've especially on the data center, because our tie-ins to the utility on basically your side of the fence would be, up at that 24 kV or higher, so that they get better rates. When your primary cost of business is power, it really matters that you pay a better rate, because it matters in the millions of dollars of operational cost a year for these data center providers, or tens of millions. I mean, it's a big number when you start getting into data usage and shaving pennies off of kilowatt hours.
Yeah. And especially like renewables, energy storage, data centers, a lot of it is in the margins. It is crazy though, seeing the amount of money that's being thrown around in the data center space right now just to secure technology, to secure power. We sometimes have developers, like data center developers or whatever, come to us and say, we got X number of this type of unit and like X number of this type of unit, and we just got what we could get our hands on. Can you make it work? And we're kind of, I hate to use the word MacGyvering, but we're kind of MacGyvering together a power system. And what's making it even more challenging, and I don't know if you've seen or talked about this at all, but what's making it even more challenging is you go from just like standard data centers where there's, large power demands to these AI data centers that have massive load swings. And it requires a whole other level of analysis in terms of like system stability and ability to react to those big load steps, because those huge load swings can have a huge impact on stability of the electrical systems, and you really need a resilient electrical system to be able to ride through that. So you're looking at things like flywheels, energy storage, stuff that can react quickly or has a lot of rotating inertia to be able to ride through some of those big load swings.
So yeah, talk about a little bit of that, for our audience on, why those types of systems would need to be installed and, where those go in and at what scale of data center do you look to put systems like that in?
So I think flywheels have been, and I don't have a ton of personal experience with a lot of data centers, so I don't want to talk out my backside on this, but just from a high level philosophical standpoint, I mean, system stability where you're maintaining, 60 hertz. So at least in the United States, 60 hertz is kind of that standard, right? So if you start to get away from 60 hertz, you can start to have some load fluctuations. There can be issues with volts per hertz that can cause some phenomena with equipment like transformers. It can deteriorate some insulation on some electrical equipment. So, but the big thing is like if you slip out of synchronism or things like that, like if a generator can't handle that sort of load step, and I mean, even if you're talking about small, high-speed generators, we're always looking at load step analysis when we're sizing our generators to make sure that if we drop, let's say it's a 500 kilowatt diesel generator, if we drop a 200 horsepower fire water pump on that, we need to make sure that that generator can handle it and maintain the required voltage that either code requires or just for stable operation that it can continue to operate satisfactorily and within the parameters of the equipment's design. So, with data centers, you're talking like hundreds of megawatts of step load. And so you need a system that can handle those, and it's in a matter of like seconds. So you need a system that can handle those sorts of fluctuations. Now, a thing like a flywheel will help you with some voltage stability and some inertia and rotating inertia, so you're not straining it. Because I think what's really happening is there are concerns about physical strain, and I think that's the part that maybe doesn't get thought about as much is the physical strain that can happen on things like turbines when you dump that much load on them all at once. Is there's a gas turbine or some sort of a prime mover that's driving all of these generators, and there's a physical force that gets applied to the rotating components of those anytime there's a massive step load because it basically transfers back through the generators electromagnetically, and that force has to get absorbed. And so there are concerns long term about how resilient and how sturdily built that equipment is to be able to handle very, very large load fluctuations.
And all these flywheels that would, and thanks for explaining that, Ryan, that helps a ton, hopefully for the audience. And so with that, I mean, I understood, but so with the flywheels, like these would all be installed at like the utility level is who's putting these in to help with those load balance, or is this on the end user to put that at the top end of their systems? Whose responsibility does that fall into?
I would say it's probably more likely that you're going to see that on the end customer because more often than not, the customer in an industrial customer or like a commercial or industrial customer situation, and we see this too with like large process facilities, oil and gas, where there may be requirements to install power factor correction capacitor banks. I would see this as no different as they have an obligation to the utility. If they're not behind the meter, at least they have an obligation to the utility to maintain a certain level of power quality. And so if they are actually affecting the grid and potentially compromising the grid's integrity, then I would see it as their responsibility. Now, again, that could vary depending on what the regulations are in those areas, but typically, maintaining a certain level of power quality is the responsibility of the end user.
No, it's good to talk through. I know years ago I Triple E did a big article around solar and solar, particularly for neighborhoods. Since and this hopefully won't go too far over the heads of the audience here, but so this will be a little technical. So with um, solar in like a whole neighborhood, for your individual house, it's not going to matter too much, but solar takes out all your resistive load, right? It's a pure DC load that's going back into your system. And so, from a grid scale at a subdivision level, what they were seeing a lot in, like, again, Southern California, Arizona, these very sunny states that have put in solar for, again, an entire subdivision. So you're looking at maybe two, three, 400 houses that all have solar during peak days. Now you have just some, I won't say pure, but it's a big imaginary load that's coming back, or the utilities seeing a lot of that instead of balanced, 80-90% power factor. They're seeing 40-50% power factor for it, which then now the utilities got to go install power factor correction capacitors to the tune of millions of dollars on the um, substation, or just the feeds into that neighborhood, to offset basically what solar panels end up doing to the power quality for it. And so at a utility scale, like at an individual house level, it's not that big a problem, but at a utility scale, it ended up being a bigger problem for the utility in particular, for a power quality issue.
Yeah, and voltage regulation, as renewables get greater penetration in the market, voltage regulation becomes a more and more important consideration, right? So you do see a lot of the utility scale solar sites where they will have power factor correction or capacitors at the point of interconnect to help provide some of that reactive support. One other application that I'm surprised hasn't gotten more traction, and it's kind of the same vein as a flywheel, but a little bit more, say, controllable. There's an application called synchronous condensers, and essentially what that is you operate it's like a synchronous machine, we'll call it. It could be a generator, usually a generator, but basically, it's a synchronous machine that has excitation controls. There's no real load on it outside of just the mechanical and windage load. So, like, it's decoupled from a turbine, and you can get them either standalone or retrofit an old turbine to do this. But essentially, it's rotating inertia that is still operating with its exciter. It's not exporting power, and if anything, it's only well, it's not exporting real power. I should clarify that. It is either importing or exporting VARs, and what that does is that allows you to better regulate your grid voltage. So if your grid voltage is really high, these synchronous condensers have the ability to absorb VARs. Whereas if your grid voltage is low and you need to support more voltage from this, you can further excite the synchronous condenser. It'll export VARs and help boost voltage in the system. Because I mean, the blackout up in the Northeast a couple decades ago, a lot of it was due to not only uh, protective device settings that were causing units to trip offline, and then there was a cascading effect of units tripping on undervoltage. But a lot of it was because the machines didn't have the capability to continue to put out the amount of VARs needed to support the grid during a dip. And so, uh, with all the renewables that are out there, whether it's in like inverter based power, so that would include solar, energy storage, anything that converts DC to AC. Um, there's really not a tried and true way to have that same effect that rotating machines would provide, short of just like static VAR compensation.
For the audience, I know this is super technical, but it's like really important to understand how, like, a lot of this works. And this is the behind the scenes, infrastructure of what needs to happen to make the grid stable, for everybody to get power, for everybody to be, happy, and the lights turn on at the end of the day, right? That's that's what we're trying to do. And then with these big loads and users, it does, it needs to happen, right? For these big users that are coming in and the upgrades to these facilities. And the one thing too, on like big mechanical loads, is if anybody's ever been in an electrical room, when massive motors turn on, you can hear the thud that comes through the gear, especially if they're on just a close contact starter instead of a VFD. I've been in a few of those, and it's like, oh wow, I did not know that electrical gear could move like that. Um, when these large motors that are in old facilities, right, like the crane rail or whatever, just kicks on, and it's like, oh, this is just a close contact starter. instead of any, nice ramped VFD, which we see for most all motors these days, but kind of fun to see those things.
Yeah, it's so I've on some recent projects worked with some fairly large medium voltage motors, on the order of thousands of horsepower. So some of our refrigerant compressors are in that 5,000 to 7,500 horsepower range. And not just when the contacts or either the contactor or the breaker closes in, but if you're ever out near a transformer when one of those starts, you can hear it groan a little bit. Because for those that don't know, on average, when a large motor starts or when a motor starts in general, um, it'll on average pull about 6 times its full load current because it's requiring, and it's mostly magnetizing current. So like it's near your locked rotor value of your motor because you're having to overcome all the torque to get started, to start rolling the motor. But a lot of that is magnetizing current, so it's a lot of VAR. So your power factor sucks. And so you're going to pull that voltage down because it's requiring so much current. You're getting voltage drop through any transformers that are upstream. And so it's a pretty high demand on that system. And so that's where a lot of that voltage support, that VAR support is so critical. And especially if you have large inductive load. The static load is one thing, but if you have large inductive load like a motor, having a really strong system is paramount. If you're near generation facilities, you're usually in pretty good shape. But if you're out in the middle of nowhere, and you have a weak system, you might have to run an analysis to see if you can even start that motor. Or the silver bullet for that one kind of tends to be a VFD, right? Like, but the problem is at that size, those VFDs can be $1, $2 million and up. So, and they aren't always necessarily the right thing. So you kind of have to evaluate it case by case, but it just goes to show like, and that's a 5,000 horsepower motor, and that's what 3.75 megawatts, somewhere in that range. Now think about that. That's megawatts. Data centers have swings of 1 gigawatt potentially. That's a lot.
Yeah, I mean, like the big scale is 1 megawatt data centers, so you're gonna see, uh, yeah, I mean, because 40% utilization is kind of what stuff's sized to. And this is the other like issue with a lot of this is like all your gear sizing is sized to max demand, but your true or your connected load, but then demand, can be, you know, traditionally it's somewhere around 30-40% for a given rack. But then you get peak times and then you got to deal with that on the utility side of things. Um, and dealing with really to feed these facilities, then it's like, okay, well, this is where the transformers should be sized. If you have let's say a 30 to 40 MVA transformer, right, where 30s, you don't really want to go above in your average demand usage. So you can swing it up, for short periods of time, but you don't want to damage the insulation too much on any of those things. So it's a little bit of a balance in like, okay, yes, it can take this, but are we going to run, what's your true demand through this plant? Are we going to have to put new utility transformers in, right? Or, 24 kV transformers, substation transformers that you're taking from the utility that you guys own at, it's coming from 135 kV or whatever the distribution voltage is there to 24 kV that you're receiving it at that, but you own it. So what do we, all that analysis to figure out, okay, transformer size, what's our lead times? Are we, doing two feeds? Are we actually getting two lines from the utility so we can double end everything and maintain operations for the facility in case, one circuit from the utility goes down? But those are all the downstream considerations that I have to think about, and coming from what you guys end up building on the power generation side. And so I guess walk us through like what does a feasibility study for some of these facilities look like? Or if you guys are doing them for like a new data center, how long should people be thinking and planning and looking at if they wanted to put a data center somewhere? Again, these are the large users, but it's not, yeah, it's a little different for like a hospital, but data centers are the big ones because you're talking in the order of hundreds of megawatts to gigawatts, which you're not going to see at like a hospital scale. But kind of walk us through that like feasibility thing and how the utility world sees these.
Sure. So I'll speak mainly to some of the feed studies we do for power generation facilities more so because I think some of the feasibility studies and the feed studies we see for the data center market, from what I understand, and there's some other people here that would probably be able to speak to it a lot better than I can that are in our on-site power division. Um, but from what I understand, at least right now, it's a very small percentage of the data centers that are have a spark actually end up turning into something just because some of them just are a pipe dream, but a few of them actually have some momentum behind them, and those are the ones that tend to go forward. But from a power generation standpoint, like this is kind of the fun part of engineering, right? Is you're having to assess multi-factor decision making. So there's balance of cost, especially in a constructability thing. So like I mentioned earlier, we're doing a lot more EPC now. We're trying to be cost conscious while still providing a very quality product to the end user. And so we work, what we've found, at least I would say for us, what works best is um, we do a lot of hand in hand collaborative front end design. We're largely doing a lot of the development, but we're working hand in hand with our clients because at the end of the day, we're handing the facility over to them and they have to own it, operate it. We want them to have input on what's going on, but we're also working with them to kind of compromise through, you know, cost considerations and complexity and sometimes simpler is better. And we can simplify things and make some engineering decisions to simplify things. So, example being medium voltage drives. They are extremely difficult to commission and they're a pain in the butt. They throw all kinds of alarms. So, if there's a way that we can design our electrical system, maybe spend a few extra $1,000 on a transformer, upsize a transformer a little bit more so we can just run across the line. There are things like that we can do, but it's fun on the front end to go from a blank slate almost, and you start to conceptualize a plant, and you think about, well, okay, what are some of the constraints I have here? Like, well, okay, maybe my pipeline gas pressure is low, so I got to put in a gas compressor, or we've got no liquid discharge, so maybe you have on-site wastewater treatment or something. So having all that stuff in play, I think it makes this fun because you're forced to think, you're forced to use your engineer brain to not only think of things from an engineering standpoint, but what's changing now is you're also thinking of it from a constructability standpoint. You're thinking of it from a cost standpoint, and you're thinking of it from a schedule standpoint. And the fourth dimension of that is you're thinking of it from an operability standpoint. I think the one thing that a lot of engineers could do better at is put yourself in the shoes of the end user and understand if I build it a certain way, can they operate it? Or if I was the operator, would I feel comfortable doing this? Would I feel like I'm set up for success here? And so that's that mindset to have, and it's a balance of all of those because you can spend a ton of money to make it like the most belt and suspenders plant in the world, and you could spend a ton of money, but it might come in late. Just ask nuclear. It might come in over budget. Just ask nuclear. Um, but not everything needs to be gold plated. Um, but it needs to be safe. First and foremost, it needs to be safe. It needs to be reliable. Those two things far and above are the two most important factors of design is safe and reliable. So yeah, it's been an adjustment in mindset over the last several years because now that we get into construction, we have to think about constructability. Can we do this in a timely manner? And so that's been a bit of a paradigm shift, not just for me, but for a lot of our division, and I would say probably for the industry as a whole.
Yeah, I mean, I think COVID really put a big emphasis on, when can you get stuff, right? What's available, and working more closely with manufacturers to figure out, oh, hey, we can actually get this piece of gear. It might not be exact, but will it work? And, a lot of things got slotted in that way because it was what people could get their hands on. And so I think in the last 5 years, everyone's been more and more aware, at least, of supply chain, how somewhat it works. Because for the longest time, most of us in the engineering world, it didn't matter. You put a set of drawings together, the contractors went and procured it, and you had submittals to review. And now, obviously, you guys are getting more in front of that on the actually procuring components for it, or like what we're doing and being partners for the electrical contractors that still somewhat of a traditional route, and the um, contractor's still going to purchase it, but we're going to be hand in hand with them through that process. And we're like reviewing product and submittals simultaneously versus going through the whole submittal process that would take forever historically. So again, shaving timelines and getting the components that you need for it. I know this I could talk on forever. Clearly, it's my job. Uh, but where do you see kind of what's the next 5-10 years? I know you've alluded to it some, Ryan, but what's the next 5-10 years look like in power distribution and power generation?
I think what's the wildest thing for me, or kind of that oh my moment, was knowing that we're selling work that's probably going to start around 2030. We hear stories from major technology providers, whether it's turbines, whatever, um, largely turbines just because of the lead times associated with those, but like they're selling slot reservations, and that's not unheard of in the past. What's really crazy is we're starting to hear of clients who are looking to make slot reservations with engineering companies to secure their services for certain time frames. And so if that doesn't tell you the sheer volume of infrastructure and generation that's going to get built out in the next several years, um, it should, because there's a lot coming down the pipeline. I would say at least the next 5 years, and there are guys that understand the market analysis a lot better than I am, so I'm just trying to regurgitate what I've heard. But at least the next 5 years is fairly reliable in terms of build out in the power market. You're going to see a lot of new gas generation. I think the other thing you'll see is an enhancement, we'll call it, of existing nuclear capabilities. I Everyone, if you look at like Vogtle and some of the other nuclear power plants that have been built, there's all kinds of stories about how much they blew schedule and how over budget it was. And I don't know that that's necessarily like the fault of anybody, like the engineers involved. It's just nuclear moves at a different pace, and it's just because of the amount of regulation that's involved. Um, but one avenue that is out there is being able to get additional output from existing nuclear facilities. Um, and so that'll be an interesting one, because if you can squeeze more megawatts out of units that are rated in that gigawatt range, that's probably a lower bar to clear than it is to build a new nuclear facility. What will be interesting to see is if the SMR market takes off. There is some momentum behind that. One of the guys that I sit with here in Chicago is really knowledgeable about all the nuclear market where it sits right now, and SMRs versus large scale nuclear, small scale nuclear, and some of the newer technologies in that. But that'll be one to keep an eye on. I think that probably though doesn't really accelerate too much until maybe that 2030 timeframe that might follow this current gas bubble. But for the next 5 years, I think gas is really going to be king, along with the continued execution and rollout of renewables and energy storage.
Awesome. No, that's fantastic. Um, and then to kind of wrap it up, because I know we're getting close here on time, is what would you say for the next generation of engineers or somebody looking to get into the industry? What's your kind of advice for the next generation?
Yeah, so this is interesting because this comes up a lot when I'm talking with either intern candidates or new hire candidates. Is they all follow the news, right? They see what's on the LinkedIn feed, they see the news about nuclear, they see the news about solar, they all want to do it. But I think the biggest thing, or the biggest piece of advice I can give anyone that's whether you're going to the power market or whatever market is just learn how to learn. Be flexible, be adaptable, learn how to learn, because what the flavor of the week is when you first start your career might not be a big thing 5, 10, 15 years down the road. Like the key is learn the fundamentals, be adaptable, be able to pick up whatever the specific market is at that time. My career is kind of a micro view of that, where I've done a whole lot of different applications in 13 years, and chances are what I'll be working on 10 years down the road isn't what I'm working on today. So it's really important to be dynamic, be flexible, and don't get stuck in any one specific area. You don't want to pigeonhole yourself in that. But the other thing too, and this is really just for engineers in general, is um, always be curious, always challenge yourself. I think one of the biggest ways that you can remain successful, remain engaged is just do what you love. Like if you have a passion for it, chase it and pursue it. And surround yourself with people that will support that because you will stay so much more engaged and do so much better work if you love what you do because you care about it. And if you don't care, then your quality is going to drop. And so I've always found that, when I'm engaged in my work, I enjoy it. That's what keeps me on the hook, right? Is I like doing what I do because I'm genuinely challenged by it. I'm genuinely enjoy it. Um, and I've always tried to find something new to learn. Being where I'm at, I've been in the power business over 10 years. I always want to be learning something new because there's so much that's out there, and I probably don't know more than I do. And like even with the experience I have, there's so much more out there to learn, and I just want to continue to absorb as much as I can. And if people have that mindset, if people have that mentality, then they're setting themselves up for success over the course of a long career.
Couldn't agree more. I mean, things change, markets evolve, right? You have the rise in renewables over the last 10 years, really, from wind to solar to, the change in power production, from coal 20 plus years ago to because of the advent of fracking, where natural gas became way more prevalent, and natural gas plants being, the leading provider of power to kind of as you mentioned, the resurgence of nuclear, and we'll see what regulations get passed to put some of those in. Yeah, no, it's being curious and being flexible in your career and not to pigeonhole yourself in something. I know in the architecture and engineering side of it, like the building side of it, is architects often get pigeonholed for like you're the rendering guy or you're the BIM guy or you're this or that. And it really shuts them off from project opportunities that they might have otherwise gotten or been a good fit for, but they got labeled as something that, even though they're good at it, a breadth of experience is helpful to round those out. So it's also key for managers to help do that too. Um, cool. Ryan, thank you so much for coming on. Is there anywhere folks could find you?
Yeah, so I'm on LinkedIn. So if you just search my name, Ryan Easterling, find me. Um, Burns McDonnell. So I was slow to the LinkedIn game. I will admit that 100%. I was slow to the LinkedIn game, but especially now being in a role where as a people manager, which I was not expecting to be doing until 2 years ago. But it's been a pleasant surprise and a blessing. But come find me now. I'm actually using it.
Yeah. Cool, man. No, appreciate you coming on. Anything else for the audience? Any last piece of advice?
Hmm. Oh, let's see here. I mean, I think the biggest thing is just stay open, always be curious. And I guess one thing too that I've always encouraged people to do is don't only learn your job, but also learn a little bit of what everyone else does. Because the more you understand how everyone else operates, the better you'll be able to operate with them. And so I've always tried to learn a little bit of what our mechanical engineers do, what our structural engineers do. The more well-rounded you can be. Now you don't need to learn their jobs and be able to do their jobs, but um, always try to learn something from somebody else in every conversation, no matter what, even if it's just a little thing, because it's just going to make you better at what you do.
That's solid. That's a great place to end the show. All right, Ryan, thank you so much for coming on. I could talk about this forever, but for the sake of time, we'll end it here. So, with that, guys, that is this episode of the Construction Corner podcast. Until next time.